about something new, hopefully today. I know that the reverse camera, the webcam is going to act up, so just remind me whenever that happens. I'll increase the volume to almost to like max. All right, let's get started. I'll keep my phone here so that I don't have to lean to take a picture. So this is Chem 8, Fall 20, Tuesday, Thursday, 9/17/2020. Maybe there is glare from this end. I'm not sure if there is glare, but I'm going to close the blind anyway. Okay. So we're talking about electronic configuration. We are talking about atoms, nucleus, shells, multiple shells, and all of that stuff. We learned 3 rules of Bohr principle. We learned Hund's rule. We also learned Pauli exclusion principle. So I'm going to go through some of the elements and write down their electronic configuration, showing them the boxes. Okay. So hydrogen, 1 box, 1 electron. Okay. Helium, 2 electrons. This is 1s, 1s. Okay. Next interesting element will be lithium, 1s, 2, 2s1. I'm going to skip the next one, that is beryllium. I'm going to skip over to jump to boron. Boron will be 1s2, 2s2, and then 2p1. Okay. Then carbon will be 1s2, 2s2, 2p2. Okay. Nitrogen, 1s2, 2s2, 2p1, 2, 3. Okay. Oxygen is important because we deal with oxygen all the time. 1s2, 2s2, 2p4. And then fluorine is also important because we deal with many acids such as HCl. HCl is like HF. Okay. Fluorine will be 1s2, 2s2, almost full, but not completely full yet, 2p. Okay. So from these elements, if we have to show their Lewis dot representation, this is how we show them. So these are the electronic configurations. Okay. These are their electronic configuration. Okay. Not writing out like 1s1, 1s2, 1s2, 2s2, 2p3, that kind of stuff, but then using boxes. It's the same deal. Okay. It's a little better because you can get down to a higher resolution picture. Okay. These are the electronic configurations. So if I have to show them in using Lewis dot representation, Lewis dot representation, I'm just shorthanding the word. I think the board is still pretty focused. Okay, this is H. Okay, This is helium. I have told you why I paired them up, because they are inactive. Okay, we'll get to that in a second. One more time. I'm going to go over that a little bit more. Lithium, 1, or is this the right representation of lithium, or is this the right representation of lithium, or is this the right representation of lithium? Okay, I'm going to give you 3 choices. Choice A, choice B, or choice C, or choice D, none of the above. In A, there is only 1 electron. Okay, this is kind of confusing. Let me just use a little different shape for the eye. That's not an electron, okay? In the first case, first answer, there is 1 electron. Second answer, 3 electrons. Third answer, 3 electrons, but 2 are paired. 1 is not paired. And the answer D is none. Which one is the correct Lewis dot representation of lithium?
A.
Sorry?
A.
Okay, one answer is A. We will talk about why in a second, but then anybody has any other answers? Or do you support that answer?
I see. Yeah, support.
Support, okay, so.
Yes, it's A.
Okay, A, okay, all right. Okay, so why these are bad answers? What's the problem? What do you put in a Lewis dot structure? All electrons or certain electrons?
Certain electrons.
Which electrons? How do you distinguish these electrons? So if I put like a black oval shape here and a blue oval shape here, which one is what? How do you name them? What kind of shell is the black shell?
Core.
The core.
That's the core. Very good. And this is what?
Valence.
Valence. Okay, very good. Okay, and we only deal with valence. Okay, yeah, great. This is fantastic. I'm really happy that you guys are on top of it. Okay, these are valence shells. So these are bad. I'm going to just erase them because, you know, this is kind of silly to have them on the screen at this point. I was just making sure that you guys are not going to make any mistakes on Tuesday. Okay, all right, good. All right, lithium. So then boron, 1, 2, 3. We don't do it, we don't pair up because we know that there are compounds that exist with as BH3. So if BH3 exists and BH doesn't exist, then we know that boron is actually keeping these electrons unpaired. Same deal with carbon. We don't do this. We don't do this, or we don't do this. Something silly like this, because then carbon is inert, right? We know carbon is not inert. Carbon can make 4 bonds. Therefore, we draw carbon as with 4 electrons. Remember, I'm going to write it down. Each chemical bond is, I would say, usually made of 2 electrons. Okay, that's very important. So you need 2 electrons to make a bond, especially when you are working with a covalent bond. Covalent bond means a shared bond. The sharing happens by taking 1 electron from this end and 1 electron from that end, and that constitutes the bond. Okay? So in order to form a bond, each element must come up with 1 single electron. the paired electron doesn't work, doesn't help. Similarly, when we get to nitrogen, the nitrogen has 5 electrons. Okay. What's the valency of nitrogen? Is it 5 or is it 3? How many things can it make bonds with? That's a question for you guys. You can unmute and answer.
3.
3 or 5? Yeah, don't use the chat. Don't give me any finger gesture because I'm not looking at the screen. Yeah.
3.
3. Okay. Somebody else? 3 or 5? How many things
3.
nitrogen can bind with? 3.
3.
3.
Okay. The reason this is not useful is because it's paired and it's called lone pair. Lone pair means lonely pair. Nobody really cares about that pair. Okay, they're left, people are generally indifferent about this pair. Sometimes it comes handy. We'll learn that later on. Okay, that's nitrogen. Oxygen is this. Okay, so what should be the valency of oxygen? How many things can oxygen bind with? 2. 2, yeah, two single electrons. Great, this is great. Okay, very good. Fluorine, valency is 1, just 1. Okay, so this is how, you know what, let me just put it in a little box or something. Okay, so these are the Lewis dot structure. This is the great saying of modern world. Hydrogen, helium, lithium, beryllium, boron, nitrogen, carbon, nitrogen, oxygen, fluorine, right? So let's make some random compounds here, okay? So these are the elements. These are the elements. If we go down to with the molecule, these are all elements. These are, if we get down to like compounds or molecules, molecules are made out of multiple elements. So one hydrogen can combine with another hydrogen and make hydrogen gas. Okay. Similarly, we have never showed it before. Do you guys think that 2 fluorines can combine with each other and make a fluorine molecule? How will fluorine molecule look like? Will it have, like, helium molecule is actually 1 helium. That's it. So this is it. When you see helium, when you fill up a balloon with helium, when you fill up a balloon with hydrogen, right? When this is filled up with hydrogen, this is what it looks like. That's inside, H2. H2 is inside a hydrogen balloon, okay? On the other hand, when you're filling up a helium balloon, it's just helium element. This is it. This is what's inside. It's not He2. That could be a trick question. There is no such thing like He2 because helium's shell 1 is full. It can't take any more electrons. Shell 1 can only hold 2 electrons. Shell 2 can hold more than 2 electrons. Okay. All right. So that's helium. Do you think what should be the formula of the fluorine gas? If I ask you, is fluorine gas like chlorine gas? Are the formula for fluorine, chlorine, bromine, iodine? What should be the formula for fluorine gas? Fluorine molecule. F2, F7. What should it be? in order to make a chemical bond, you need two unpaired electrons. So what if two fluorines come across each other? Do you think they can make a legitimate bond? I'm just using different shapes to designate their electrons. So fluorine 1 and fluorine 2, they come together. Do you think they can share that unpaired electron to make a fluorine molecule? Does it sound reasonable to you guys?
Yes.
So looks good to me. So that this formula should be F2. This is how fluorine gas is. If I ask you in the exam, what should be the formula of chlorine gas? You shouldn't be freaking out. You shouldn't be like trying to figure out, oh my God, what's the electronic configuration of chlorine? And it involves D shells. So I'll have to write down Aufbau principle and I'll have to write the whole darn thing to figure things out. No, you're wasting your time because fluorine, chlorine, bromine, iodine, they are in the same column. You should know their outermost shell electron numbers or valence shell electron numbers. What's the valence shell electron number for iodine? Let's deal with iodine. If I ask you, write down the formula of iodine gas or molecule and show the Lewis dot structure. Lewis dot representation. What does the iodine's Lewis dot structure look like in the molecular form? What should you do? Should you write down the Aufbau principle and figure out like its electronic configuration because it's like shell 1, shell 2, shell 3, shell 4. It's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 5p6, so on and so forth. 5p4, 5s2, 5s2, 5p, sorry, 4s2, 4p5. That's going to be the formula for iodine. Okay, I'm wrong. We will have to go down to level 5 because fluorine is level 2. Chlorine is level 3. Bromine is level 4. Iodine is level 5. Yes, 5s2, 5p5. But if you're doing that, you are really walking on the wrong path. You already know the shortcut. The shortcut is how many electrons does iodine have in its outermost shell? Valence shell. What's the number? Fluorine, chlorine, bromine, iodine. This is what fluorine looks like. This is what fluorine looks like. How should iodine look like in the Lewis dot representation? How many electrons shall I write around iodine?
5.
5? Somebody else? I want to hear from more students. One answer is 5. Is that the right number? We have talked about it. Are you guys not paying attention? Are you not listening to the videos? I don't usually go back and see how many hits I've gotten, like how many people have actually watched it. If you think that sitting in the Zoom and watching the colorful show is kind of like watching a stand-up comedy or something like a TED Talk or whatever, it's not going to cut it. It's not going to do it. I'm not trying to be negative here. And nothing has triggered those thoughts, but I'm just saying that right before the exam, if you guys are clueless, it's going to be the end of the story may not be very pleasant. And I want the end of the story, end of the semester to be pleasant and happy ending. I want it to be a happy ending. I'm a very positive, optimistic person. I don't lose my optimism or my resilience or conviction in the worst case scenario. When nothing is working, I still try to stand up and keep running, keep walking. If I can't run, I would rather limp, but then sit still, okay? So what I'm trying to tell you is that you need to earn your grade. If you're thinking about just passing this course because chemistry is not your cup of tea, that's totally fine. I am not upset if that's the case. Okay. So in order for you to pass, you can't cheat away your way. I mean, I don't know what your plans are. Hire someone to take the quizzes. If you do that, I know that I'm not using camera. You can probably do that, but it's going to come back and bite you in a big way. You might pass this course, but you might not. It might not be. It's going to come back and bite you down the road. I'm not trying to threaten you about with a philosophical or religious, twist in it. I'm just saying what I've seen in my life. What goes around comes around. Whenever I have done something wrong, I have been punished. Okay, when I have done something like maybe a little borderline right, wrong kind of a thing, I have been punished afterwards. I've seen that with other people. I mean, who have hurt others. It usually comes back. So please, without talking about the negatives, it really hurts me when I talk about this stuff like cheating and fudging and stuff like that. I don't like to talk about that because I like to trust you and I like to be trusted and I want the other party to reciprocate the same way. The worst feeling that I feel is when I feel that someone is deceiving me. And the deceit can come in many different ways. It can come from a family member, it can come from a friend, it can come from an employer, a fellow colleague, it can come from students too. So I would really appreciate if you are honest and straightforward and following the basic human values and learn. This is not that difficult. The way I'm breaking it down, I don't think it's not like rocket science. You have to remember formulas and really calculate air pressure and turbulence and all that stuff. Okay. Fluorine, chlorine, bromine, iodine. What's common down the column? Let's go back. I don't really care if we don't cover like 5 chapters. Whatever, if we cover 3 chapters in this whole semester, I want you guys to understand and be able to apply that concept. That's my goal. What's common down the columns?
The amount of valence electrons per column.
Say that again, please.
The amount of valence electron in each column.
Yeah,
like
the
the
number
first
of,
column only has.
Yeah.
Yeah.
Okay. So let me just, maybe this is not helping. It's not helping you because I don't have the periodic table in front of me. Okay. So helium, neon, argon, krypton, xenon, hydrogen, lithium, sodium, beryllium, magnesium, carbon, silicon, boron, aluminum, nitrogen, phosphorus, oxygen, sulfur, fluorine, chlorine, bromine, iodine. If fluorine, how many electrons does fluorine have in its outermost shell?
7.
Okay. If that's the case, how many electrons should iodine have in its outermost shell? Somebody else should answer. 7. Do you guys see the point? Do you guys see the connection here? You learn something and then you put it together, right? You learned that down the column, the number of valence electrons are the same. Number of valence electrons are the numbers of dots you put around an atom with its letter representation, F, C, H, E, N, and that's how you represent the element. Why do we do that? Because those are the electrons that are important when it comes to bonding. When we talk about ammonia, when we talk about an alkane, CH4, bigger alkanes, this is just the beginning. We are really dragging our feet with this fundamental knowledge because I want you guys to understand it very well. After this, it's going to get more complex. We're going to talk about large alkanes, alkenes with double bonds, that's different kind of scenario, alkynes with triple bonds. Then we'll talk about acids and bases. Then we'll talk about molecules that are mirror images. Then we'll talk about halogenated compounds, making different compounds out of those compounds, doing elimination reactions. How do you make a double bond from something else? This is in our plate. Then we'll learn about alcohol. Then we'll learn about carbonyl compounds, a carbon with a double bonded oxygen. So this is all left over. I mean, you're kind of going very slow at snail pace. And my plan is to pick up speed after the foundation is built properly for everyone in this classroom. I don't like to leave anyone behind. I want everyone to pass this course. You don't have to get your A's if you're really not into it or you can't do it, but I want everyone to pass this course. I have had many times in Chem 8, not in virtual session, when people are doing funny business, I have seen that, everybody passed. In the recent years, when I've been teaching a lot of Chem 8, I didn't have to fail anyone. Somebody, I think, withdrew from the class, but that was a different scenario. So please pay attention. I understand it's a lot going on, and you may be depressed because of the pandemic, but cheer up. I mean, we all have problems. Unless you cheer up and keep moving, nothing is going to be given to you like just by itself. I'm not going to give you a grade because you sat there in the Zoom and with your camera off. That's another thing that I stopped bothering you, because I don't want to force anyone. But that there are certain rules and regulations. Like I know that this is the country of, this is the time of division. If there is a government mandate, people like to not follow it, or people don't like to listen to the scientists. And this is the crazy time. I'm not being politically polarized at this point. Okay, how many electrons around iodine?
7 valence electrons.
Watch the old videos and figure it out. Read the book and figure it out. I can't go back and repeat over and over. So iodine will be an identical scenario. 2 iodines will come together and it's going to look exactly the same. The only difference is that these electrons belong to level 5, shell 5. These electrons belong to level 2, shell 2. For chlorine, they're going to belong to level 3. For bromine, they're going to belong to level 4. Okay? Let me ask you a question, a random question. I just want to see if you guys can connect the dots. Fluorine let's use that same color that I have used. Fluorine, chlorine, not that chlorine is green. Fluorine, chlorine, bromine, and iodine. Okay? If you think about the atom as a little sphere, if you think that this whole atom with the nucleus in the middle, and then you have the shell 1, then you have shell 2. Fluorine is what? 1s2, 2s2, 2p5, right? So it goes up to shell 2. So if the size of this atom is, if I'm representing the size like a little round ball, like a little sphere, okay? Is chlorine, bromine, iodine, is chlorine going to be smaller than that? Which one is the right representation? The left or right? If this is A answer, this is answer B. Which one is the correct representation of chlorine? The left or right? You can unmute and tell me A or B or left or right. The one that's correct.
Can you repeat the question?
Is the size of chlorine atom, fluorine atom is about that big. Let's say an inch diameter. What I have drawn for chlorine's representation as a sphere, this is, let's say, a centimeter, half an inch, and this is 1.5 inch. Should chlorine be bigger than fluorine, or should chlorine be smaller than fluorine? You should be, everybody in
I'm
this
not
class
sure,
should be.
but I think it
Bigger.
should be bigger because it has more proton and neutrons. I assume.
I'm hearing, I'm trying not to be judging at this point. I want to see if others want to participate. What do you guys do when you turn on the Zoom? Like, are you like taking a nap or laying on the bed, or what's going on? I mean, are you looking at the screen and paying attention, or
It's bigger.
bigger?
I think
Thank
it's
you.
B.
Big? Can someone think about it, and let's say I am being really nitpicky, and there are 3 points for articulating the answer, like justifying why is chlorine bigger. So you guys are saying this is not right, this is right. So you're saying that chlorine is bigger than fluorine. How would you explain it? Let's say this is like a little project. You have gone to Shark Tank. You're trying to get like $100 for doing some experiments at an elementary school, at your sister's school or nephew's school or niece's school. And this knowledge is important. And you are trying to tell them that, well, chlorine is bigger than fluorine because you have like 2 minutes to explain. 5 sentences. How would you explain? I'll give you like half a minute or 1 minute to prepare. So figure out your speech in your mind, and then explain that using minimum words. You have very limited time. You really have to impress upon the Shark Tank guys to give you $100 or some investor that why chlorine is bigger than fluorine. How would you explain?
Has a higher atomic number, which means it has more protons and more neutrons. And if it has more protons, then that means there's a larger amount of electrons in the electron cloud.
We haven't talked about the nucleus being bigger or smaller when you have more protons or not. And if the nucleus is bigger, that doesn't guarantee that the whole atom is going to be bigger, okay? So you have pretty much focused on the size of the nucleus by talking about protons and neutrons. That's not going to cut it. What's outside the pit of your peach? The electrons, okay? So focus on the electronic situation. Fluorine and chlorine. What do you think is going on with fluorine and chlorine and bromine and iodine? Think about the shells as layers. One layer, one bubble, another bubble. Maybe an inch from that smaller bubble. Then a third bubble, an inch from the second bubble, right? So use that analogy and explain again. Why is chlorine bigger than fluorine?
Chlorine is bigger than fluorine because chlorine's shell is on the third of 3p5, while fluorine has a smaller shell on the second one, which will be 2p5.
Sounds good. So you're adding a new shell. So this is shell 2 for fluorine, 2s2, 2p5. For chlorine, it's 3s2, 3p5. For bromine, 4s2, 4p5. For iodine, it's 5s2, 5p5. So you're adding one more layer, another layer, like an onion. Think about it like an onion, but different layers. Skins have air gap, as if they're suspended in space. One layer of onion, then there is nothing but some mushroom-like fluffy material. Then another layer, then another layer. So if the onion has 5 layers, it's going to be a bigger onion than the onion with 4 layers, than the onion with 3 layers, than the onion with 2 layers. It's just connecting the dots. If you guys are paying attention, I don't think you will have to really study. I mean, I think I break it down. I try to break it down to the very low level. Okay, bromine should be even bigger. Bromine atom should be even bigger. And iodine should be even bigger. Okay, so this guy is 2s2, 2p5. This guy is 3s2, 3p5. Bromine is 4s2, 4p5. And iodine is 5s2, 5p5. So the reason I'm taking this deviation and discussing this material is on Tuesday, you might expect something like this. I might ask you to draw the Lewis dot structure of something or analyze or investigate a Lewis dot structure of something that we haven't covered in our lectures. And I don't want you guys to like freak out and have an anxiety attack. Like, oh my God, I don't know how to deal with iodine. It's the same thing as fluorine. Bromine it's going to be your, instead of writing F, you will be writing B, uppercase B and a lowercase r, and 7 electrons, same deal. So if I ask you something about sulfur, if I give you a copy of the periodic table, okay, if you have access to the periodic table, it's open book. You can open up the periodic table. You can have a printout of the periodic table available at your just make sure that you can access it. Have a printout. Periodic table is on Canvas. So I would probably do that before I'm taking the exam, and then look up. If I'm asking you something about silicon, you shouldn't be freaking out because silicon is just like carbon. It's not just like carbon, but we're not talking about the nitty-gritty property differences between carbon and silicon. We are just dealing with Lewis dot structures and some simple stuff. Okay, so silicon and carbon very similar. Boron and aluminum very similar. 3 electrons, 3 electrons. 4, 4. 5, 5, 6, 6, 7, 7, 7, 7, 7. These guys are all pretty much full. Helium is 2, but down below helium, they're all 8 electrons. Okay, so far so good? Okay, so let's keep moving. So my plan for today is something little different. I don't want to harp too much, bog down too much with this business. So this is how you write the molecules. This is how you represent the elements in using Lewis dot structure. You don't bother about their valence core shell electrons. You only care about their valence shell electrons. And if you have paired valence shell electrons, they're not used for making a bond. You only use the single unpaired electron in the valence shell to make a bond. Got it? Okay. All right, so let's talk about some simple molecules which we have talked about like so many times so far. So I'm going to ask you, this is hydrogen and this is boron. Okay, we have discussed it many times. So let's get over with it as quickly as we can. What should be the formula of the smallest molecule made from boron and hydrogen? Minimum number of boron, minimum number of hydrogen. What should be the formula of it?
BH3.
One answer is BH3. Okay, somebody else?
I support that.
Support that, same BH3. Somebody else? There are a whole bunch of students in this class. I mean, I know being introvert is one thing, but participating in a class is also important. I don't know if I come across as an intimidating person. I think I'm pretty friendly, but then obviously today maybe I'm little disturbed. You know why? You guys know. So maybe that's why my tone is a little different, but hopefully on Monday and Tuesday I'll go back to my ground state. My electrons are a little unpaired right now for some reasons that many of you can probably relate to. Why? Okay, BH3, is that it? That sounds good? Yeah, somebody else?
Yes.
Okay, sounds good, thank you. Okay, so BH3 it is. BH3 That's BH3. All right, let's get to the one that I really want to spend some time on. Carbon and hydrogen. Okay. How many carbons and how many hydrogens will make the smallest hydrocarbon? To make the smallest hydrocarbon, how many of each material do you need?
CH4.
Awesome, thank you. That was very, very well said. Viviana, loud, clear voice, like that. That's how you should be answering. Don't be afraid of me. Even if I'm mad at you, I can get to you. This is all computer screen. All I can do is I can take my frustration out on my computer screen. Okay, CH4, that's great, fantastic. How do we know that? Because of the, we have isolated this compound from wherever. Somebody analyzed it and found out that it's CH4, not CH or CH2 or CH3, okay? And this is what its Lewis dot representation looked like. This is what the molecule looks like. This is what it looks like, right? Now, so what I'm going to do right now is I'm going to spend some time on CH4 and teach you guys some new concepts that are called hybridization. Hybridization, don't be intimidated by the word hybridization. Hybridization is nothing but mixing, okay? One part of something with three parts of something else, or one part of something and two parts of something else, or one part of something and one part of something else, okay? It's really straightforward. So what I'm going to do is I'm going to take a picture of the board because I'm going to erase pretty much everything on the other side, on the right side of the purple wiggly line. So let me take a picture. And feel free to ask me any questions at this point, if you have any questions. Okay. You guys are comfortable with what you have seen, and I would recommend that if it's okay to be falling behind for whatever reason, whether you are playing video games or you are trying to help your parents with multiple jobs or you are taking care of the niece and nephew in the house, because I understand that when you are at home, you probably have the to-do list like significantly elongated than what it used to be when you used to come to school. So I understand that, but then please, please, please study this weekend. If you don't study this weekend, you're not going to be happy on Tuesday, okay? All right, so I'm going to erase this side, okay? And I don't think we will need to remind ourselves who we are because we kind of know, and the video will have that up there. And so let's focus on carbon and see what's going on in the middle of carbon atom. And can we explain the phenomena? Can we explain the results, the evidence of different compounds' properties? And can we figure out, like, what's going on inside carbon? That's exactly how science progresses. Okay, so now, you know what? Let me just erase this and start kind of fresh. Okay, hydrogen and carbon. This is hydrogen. This is hydrogen, 1s1, okay? This is carbon. Okay, if I have to draw the Lewis dot representation, this is what it'll look like. and the electronic configuration. I can actually skip the 1s sometimes. Sometimes I just show the 2s. I think it'll probably take you guys a little bit longer. So I'm going to draw the 1s anyway. 1s, 2s. And there is a reason that I will draw the different p orbitals in different color. I'll explain in a second. Why am I doing this? Okay, blue, green, and empty red. Okay, I'll just call them 2p level. So this is 2s and 2p. All good? You guys are fine? So far, so good. Let me just check your background knowledge, the knowledge below at this level. Okay, try not to look up in the book or in anywhere else. Just try to answer what you see based on what you're seeing. 1s2, 2s2, 2p2. What's the atomic number? Don't look up on the periodic table or don't look up on Google. What's the atomic number of carbon?
6.
1s is 6. I'm hearing. I'm trying to keep a neutral face so that I'm not trying to send you a message, right or wrong. What's the atomic number of carbon from this electronic configuration? Somebody else?
I support her answer. 6.
Okay. Maybe one more or two more answers. 6?
6.
Okay.
I agree, 6.
Okay. How do you figure that out?
By counting electrons from the arrows.
So you just total the electrons, sum the electrons, right?
It should equal amount of protons, usually.
Important point. That's good. Okay. So someone said I can't read the name, and I haven't learned your names with their faces thanks to the virtual world. Total number of electrons. So atomic number, carbon's atomic number of carbon is 2 plus 2 plus 2 equal to 6. Okay. You count everything. You count everything because these 2 are core, these 4 are valence. I'm just going to pause for 10 seconds to make sure that you digest that. Those two electrons are in core shell, 4 electrons are in valence shell. Are you clear about that? Can you remember it even in your dreams? When you wake up, if someone asks you, how many core shell electrons does carbon have? You have to answer 2. How many valence shell electrons does carbon have? The answer is 4. And that's represented here, 4 electrons. We don't discriminate. We don't count s orbital versus p orbital. They're all in the same level, right? I'm going to get out of the screen and just let you guys kind of like look at it and make sure that you get it. Okay, this is old stuff. This is simple stuff. Okay. So if I ask you a question, simple question, there will be lots of simple questions on Tuesday, maybe a few hard questions, but not beyond the boundary of what we have learned so far. Maybe 1 or 2 questions, there will be difficult, okay? Difficult questions like you will have to really think beyond your understanding. You'll have to really take the concepts and apply it and get there. So even if you don't get that, you will still be in the A range if you get the other normal average questions taken care of properly, okay? How many types of shells are in carbon? 1, 2, 3, 4. What's the right number? How many kinds of shells are present in carbon's electronic makeup?
2.
What are they called?
First shell and second shell, which is
Well,
the core and valence.
core and valence. Okay, very good. Just checking. Okay. All right, that's good. Now, this is the ground state. We have talked about it. This is the ground state. Not good enough to explain why this happens. We all know that this happens, right? We know that the formula of the smallest hydrocarbon is CH4. That means there are 4 CH bonds. That means there are 1, 2, 3, and 4 CH bonds. If there are 4 CH bonds, that means carbon is providing with 4 single unpaired electrons. That's not how it looks like. This is the valence shell. Okay? Does it look like that? I mean, if this is correct, then it should only form bonds with 2 hydrogens. So something happens, right? The ground state goes to excited state. Excited state, where we usually write as, looks like an Amazon sign, but turned upside down. Carbon star, okay? Carbon star means excited state. I'm going to just not bother about 1s from now, okay? 2s, two P, another 2P, okay? So this is 2s, and these guys are 2P, okay? So what's going to happen? One of these electrons is going to jump up. Okay? Now it makes sense that carbon can provide with 4 unpaired electrons. So you need to untangle, unpair these 2 guys, and it goes in there upside down, flips, because you want to keep maximum spin according to Hund's rule. So it goes up, and then you have 4 unpaired electrons. This is not correct. So this is the excited state, and now carbon is ready to bond. Carbon is ready to bond with hydrogens or whatever else. Okay, now the next question is, this is where we kind of stopped in the other class yesterday, okay? The next question is, I'm going to try to do something that I'm very uncomfortable with, give you a physical glimpse of how these orbitals look like at S and P level, okay? And then I'm going to ask you a question. All right. Okay. I'm not comfortable because I know that this is not really right, but we'll have to do that anyway.
What?
I'm going to draw like 3 axes. X, that was a terrible straight line.
Oh, no, straight. We all can't draw straight lines here, bro.
Maybe you can unmute you can mute yourself. You don't have to be here, you know. If you're too tired, maybe you can take a nap. Turn off the Zoom. I'm not forcing you. Okay, X, Y, and Z axis. The X axis is parallel to the whiteboard. The Y axis is coming toward you. And the Z axis is vertically upwards. Okay? X, Y, and Z. All right? The S orbital The s orbital, the 2s orbital, looks like a tiny sphere, okay? Pretty small, like a little tennis ball. At the center of the three axes where they're cutting each other, right? X is parallel to the whiteboard, Y is coming toward you, perpendicular to the x-axis, and Z is up and down, north, south, okay, up, down. That's how the s orbital looks like. It's like a sphere. One of the three p orbitals, all the three p orbitals, they look like dumbbell like a lobe here and a lobe on the left hand side. I'm going to put some shape. So this is the p orbital along x-axis. Okay. This is the p orbital along the y-axis. Okay. And this is the p orbital along z-axis. The three orbitals. P orbital is significantly, listen to the word that I'm trying to hint at you. Each p orbital is much longer than the s orbital. Okay, this is tiny, this is long, right? So supposedly, one electron is sitting in here, one electron is sitting here, one electron is sitting here, and the fourth electron is sitting here. I'm going to change the color to red. Okay? So far, so good? If that's the case, if this is how the excited state carbon is binding with 4 hydrogens to make CH4 bond, providing the CH4 molecule 1 electron from here, 1 electron from here, and 3 electrons from the 3p orbitals, I'm going to ask you guys a question. What should CH4 look like? If I'm going to give you 4 options. Let's say the hydrogen, I have to change the color of hydrogen, unfortunately. Let's say the hydrogen is orange. I should have thought about it earlier. I didn't. This is CH4 in one representation, all equal bonds. This is representation A. In the second case, okay. In the second case, one bond is long and 3 bonds are short. This is case B. And case C, carbon one bond is short and 3 bonds are long. I'm trying to be as accurate as possible, but you know, picture is not going to be perfect. Okay, this is C. Okay, if in CH4 the excited state carbon is using an electron in the one of the 2 s orbitals, the 2s orbital, 1 electron is coming from one electron is coming from the 2p x orbital, one electron is coming from the 2p y orbital, and one electron is coming from the 2p z orbital. Okay, they're there. P orbitals are longer than the s orbital. If that's the case, what do you guys think? I have muted everyone. What do you guys think? Should the 4 CH bonds be equal length? Should 3 of them be short, long? Or should it be short, long? Which one? If you have read the book and you know what happens in the real case scenario, please try to control yourself and not answer. I want you to answer based on what we have learned so far, not what actually happens. In reality, something else happens, but I'm trying to make a prediction based on our knowledge so far. If this is the case, if this is how the orbitals look like, and one electron in that bond is sitting in s orbital, and the 3 other bonds are provided by the electrons in the p orbitals, then which cartoon representation is correct? 4 identical bonds, 1 long, 3 short, or 3 long, 1 short? You can think about it for a minute or two. Connect the dots, connect the concept, the learning on the right side, and apply it to the problem. Okay. Anybody has any question, any answer, any idea? Which one is the correct answer? A, B, or C?
C. 1 short, 3 long.
Okay, one answer for that. Spencer, thank you. Anybody else?
I would say C as well.
Okay. Anybody else?
I agree with C as well.
I don't know if 3 is a true representation of the entire class, but then that's the right answer. Okay, so this is the right answer. Okay. Can somebody kind of articulate if it was a free response question, and I might still have like some kind of free response answers, maybe 2 of the free responses in those wrong answers will be all convoluted and some leading to some confusing state of mind, but 1 will be the right statement. So you need to read and figure it out. Can someone like explain why 3 bonds should be longer than the 4th bond according to this setup? Anybody, even if you have, you are one of the answer givers so far. I think Allison, Spencer, and somebody else.
The way that I articulated it was like the s orbital is like smaller, so it doesn't reach as far out from the atom.
Keep going.
It doesn't reach as far out from the atom, and then the p orbitals, they reach farther. So I just assumed that the S would be short and the others would be long.
Perfect. It's that simple. Yeah, that's it. That's it. Perfect. Who are you? Spencer. All right. Yeah, that's great. Because this is the 2s orbital. This is the 2p orbital, 2px orbital, sorry. This is the 2py orbital, and this is the 2pz orbital. And this guy is the tiny, tiny little thing. If this is the tiny little thing, and this is the long thing, and like infinity, and this is this, and that's this, right? They're much longer, right? So yeah, that's perfect. So that's the prediction. That's what you have predicted before you measured the bonds in a real methane molecule. All right, next question you are supposed to answer based on your gut feeling, okay? Yeah, this is perfect. This is predicted. And perfect prediction, I like it. This is what is predicted. In real life, I'm not going to write the whole thing. You understand what I'm trying to say. What is the right representation of CH4? Is it A, or is it B, or is it C? I know that it's hard to answer. If you have read the book, try to control and not answer. Let others kind of predict. What do you think in real life? The bonds are equal, 3 are short and 1 is long, or it's actually the way the prediction is? Which one is the right representation in real life? When you take methane and measure the bonds, what does it look like?
So it would be different than the predicted?
I'm not going to tell you that.
Or would it, that's the predicted, but it would look more like A when you look at it?
Okay, one answer of real life scenario is this. So Spencer, you're saying that in real life, all the 4 CH bonds are equal, same length. That's what you're saying, right?
Yeah, or they're close to equal, and you can't really determine the difference.
So it should be 3 long and 1 short, but one prediction of real life is that in reality, that's not the case. They're all equal. How many of you support him? Speak up. Don't write anything on the chat. I don't even have the chat window open, chat box open. You think he is right or he's wrong? Anybody wants to say something? I know it's just a wild prediction, right? One other person?
Can I say something real quick?
Yeah, please.
So would this be observing the compound in real life?
Yeah, I mean, let's say this is the prediction of based on your current knowledge. Then you isolate methane, right? You go to a marshland and you bring balloons or whatever ways you capture methane. Then you come back to your lab, purify methane, because methane is mixed with nitrogen and oxygen and whatnot in the air, all kinds of garbage. You clean up methane, make sure that you only have methane. Then you do all kinds of experiments. You can do infrared spectroscopy. You can do some other studies to figure out how many types of absorptions are happening. If there are 2 types of bonds, long bond and short bond, it's going to when you pass infrared radiation through a molecule, the different bonds start dancing. Okay, they contract and they expand, and they also bend. Depending upon those absorption of infrared spectroscopy, the radiation, electromagnetic radiation, you get different peaks in the infrared spectrum. This peak means this particular bond is stretching and contracting. That peak means it's bending. Okay, and bending can happen in different ways. I mean, we are not going to teach you infrared spectroscopy in Chem 8, but in Chem 128B, we teach that. So looking at that, scientists can tell, are all 4 bonds equal? Are there 2 types of bonds? 3 long, 1 short, 3 short, 1 long, things like that, right? So when you do that experiment, it actually turns out that your prediction, your wild prediction was right. This is not how, in real life, this is not how it looks like. This is not how it looks like. In real life, all 4 CH bonds are identical, same length, okay? Real life, all 4 CH bonds are equal. Okay. I want to see if somebody in this class, or 1:42, we still have 8 more minutes. So this is the deal. Okay, this is reality. This is what it is. But so far, our knowledge tells us otherwise. Our knowledge says, man, that's not right. How can 4 bonds be equal? Because 3 electrons are coming from similar kind of anchors. It's like a crab with 3 long legs and a short leg. Okay, I know the crabs, you know, the arms are different lengths. One is short and one is long. One of my students is making a compound that we always refer to those compounds as crabs because it's got unsymmetric arms. So 3 long arms and a short arm. If 3 long arms and short arm is how carbon looks like in its elemental stage, then this should be correct. But in reality, that is correct. Okay. So if you are a scientist and you are, you know, let's roll back time like 100 years, or I don't know the exact timeline. If you're at this juncture of scientific progression that you just stumbled upon the fact that, oh my God, I predicted this, but in real life, my colleagues have measured it in Switzerland, and they're saying that all 4 CH bonds are similar. How would you tweak the theory? What would be your next theory or hypothesis that you're going to mess with this concept and you're going to say something else happens to carbon's electronic scenario so that methane has 4 identical CH bonds? Can somebody think that that would be a bonus question? If we only learned here and you're taking an exam from the knowledge up to here, I might ask you a question that, what do you think happens? That's really like pushing your limits, okay? So I'm pushing your limits right now. What do you think happens right now? And I have a really bad metaphor that you always use, you know, like you have 1 part beef and 3 parts chili, and there are 4 kids in the house, and they want identical food. So think about it this way. I'm going to use the same color. I'm going to just drop a hint. I'm not going to give you the answer. So there is a house. The mom has 4 quadruplets or whatever they're called, and there is 1 bowl of meat, beef, and there are 3 bowls of chili. Okay, identical. I'm not trying to send any message by drawing a different kind of a bowl. Okay, and let's say there is chili here, the beans here, sorry, beans. And the mom first thought that, you know, Joe likes meat, I'm just going to feed him the beef, and they can be vegetarian, the rest can be vegetarian. I'm just going to throw them the bowls and just going to warm it up. And they say, we want the same food. You know, they don't want different food to be given to different people. You know how toddlers can be. They can be real pain in the neck. They want the 4 kids. Four kids want identical food. Otherwise, they're going to throw things upside down, and at like 7 p.m. You know, Friday night, nobody's going to be able to sleep at night because they're rambunctious children. If you don't do what they're asking you to do, the poor single mother will be having the hardest time of her life, and it's going to completely ruin everything for that evening, and it's going to ruin the weekend. So what do you think she will do? And similar concept applies here. Think. How do you make chili?
You mix them together.
You mix them together, right? You throw them in a blender. You put that in the blender, and you run it for like a minute, and you saute it and fry, you know, with onions, and put some spices and blah blah blah, and oil and whatever else goes in there. That doesn't happen in the real case scenario. And then whatever material came out of that, you know, after you put it in the blender, you cook it, or you use a crock pot or whatever it is, right? You come up with something, okay? That mass of that material will be 1 part beef and 3 part bean, right? Beef and bean, 1 part beef and 3 parts bean. And that will be, you know, when it comes out of the bowl, in the big container, it looks like the chili. This is the chili, okay? So you put that much of that here. This is the chili, okay? And each of these 4, the quarter part of that entire chili has, if I can name them, so let's call the beef B, and let's call the bean N. This is N, okay? So whatever you made the chili from, it has 1 part B and 3 parts N. So how would you kind of set up an acronym for that chili? So it's going to be B. It's going to be B N3, right? 1 part beef, 3 parts bean. Okay, BN3. This is going to be the same deal. BN3, BN3. 1 part bean and 3 parts. 1 part beef and 3 parts bean. So they're all going to be called BN3, 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 BN3 because it's a chili made from 1 part beef and 3 parts bean, and mixed together, whatever, and then divided into 4 identical parts. And if you total them, if you weigh them out, the total weight of that will be the total weight of what went in, okay? If you started with 10 grams of that and 15, 15, 15, 45, 55 grams, then over here you have 55 divided by 4, whatever that comes to, 11 point something or 15 point something or 16 point something in each of them. The total mass doesn't disappear. So using that beef and bean to chili example, what do you think will happen here so that the bonds in CH4 are all identical? What do you think will happen to the orbitals? Nature will do what? Nature is the mother of all things that happen under the surface of Earth, on the surface of Earth, under the surface, under the sky, right? So what does Mother Nature do? What do you think will happen to the s orbitals and the 3p orbitals? That's how we explain it.
Do they all get put in the same orbital?
They will mix, basically. So the bottom line is these 4 orbitals will mix and produce 4 identical mixed orbitals. Okay? This mixing, that word that we use when we talk about orbital mixing is not mix. That's too, colloquial. We don't use the word mix. We use a different word, like a car that uses gasoline engine and electric battery, electric engine. What are those cars called?
Hybrid.
Hybrid. So this process is called hybridization. When you hear the word hybridization, you think mixing. It's that simple. I have had trouble teaching hybridization in the last 12 years. Somehow I haven't cracked the code yet. Okay. Somehow my students don't understand it very well. I don't know, maybe it's my fault. Hybridization is taking 1 part S and 3 part P, mixing it together, hybridizing them to produce 4 identical orbitals. Why are we talking about that? Just to explain this phenomenon. That's it. That's the only reason. It's result-driven hypothesis. Because the 4 bonds in CH4 are identical, we have to tweak our theory a little bit. This doesn't cut it. Not enough. This is not enough. You need to figure out something that they must be mixing together, hybridizing to produce 4 identical orbitals. And what should be the formula of the 4 hybridized orbitals? 1 part beef and 3 parts bean became BN3. So how should we call these orbitals? This type of mixing, 1 part S and 3 parts P. How should we call it? S, P. What's the number? What's the integer should I write? 1, 2, 3, 4, 5. 1 part S and 3 parts P. That means SP.
3.
3.
SP3, 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 and SP3. So now everything is great. We just came up with a great idea, the $1 million idea that, oh, how do I solve the problems? How do I feed my 4 children and they don't start driving me nuts? They're all happy. They look at each other like, what did he get? What did he get? He looks at mine like, what did I get? Yeah, we all got the same thing. They all look the same. Nobody got more than the others. They're identical amount. They're served in the identical bowl. They're given with the same spoon, identical spoon. They're all happy. They're like, okay. Nobody's getting a better deal than I did. So everybody is happy. All the 4 bonds are identical because they're coming from the same type of orbital. Okay. In reality, does it really happen that way? Who knows? But it helps us explain the result. That's how science progresses. We don't believe in faith or trust. It's all science and evidence based. You have some result and you're trying your best based on your knowledge to explain that phenomenon. Somebody else comes back and says, that's nonsense because it's not a particle, it's a wave. So what are you talking about? When I talk to my next door collaborator, Dr. Krishnan, he's a physical chemist. Actually, his PhD is in physics. He says, hybridization, is this how you draw the molecule? Shantanu, ho. He literally, we are friends, so we make fun of each other, okay? but generally the physicists are mathematicians are the smartest, then physicists, then organic chemists, then, well, inorganic chemists, then organic chemists, then other people. I'm not going to mention, okay? The physicists are smart, much smarter than us, okay? So this is how hybridization happens. And I don't want you to be intimidated by the word hybridization. Hybridization means mixing. And how do you come up with the great idea of sp3, a big S and a small p and a 3, number 3? Well, 1 part beef, 3 parts bean. So 1 part beef, B, 3 parts N, 3. That's it. The 3 means how many N's. And you could have said, why don't we write, Dr. Maitra, why don't we write this? Yeah, because we just don't write the S, the 1. You never write the 1. So there can be 3 kinds of hybridizations, sp3, sp2, and sp. We will talk about it down the road. I think this is probably enough. So there will be a review tomorrow at 5 p.m. I'm going to share the Zoom link. It's going to be combined with the Monday, Wednesday, Friday class. It's going to be also recorded. If you come to the review, be prepared to do something about solving a problem. I'm not going to be lecturing. No lecturing. I'm just going to put up a problem and I'm going to see if you guys can solve the problem. I'm also going to finally upload some homeworks. I don't want you to freak out if you see something that doesn't really make sense we haven't covered. I'll write an announcement with that. Some of you wrote to me that you guys woke up pretty late and you wanted to retake the exam. I'm not going to throw that exam because I looked at the statistics and all the questions were attempted. So I am not going to do that. So we will have the quiz. We will have the exam on Tuesday. We'll have the review on tomorrow. If you want to have one-to-one Zoom meeting with me because some concepts are confusing, see if you can make it to the review. If you cannot, reach out to me and we can probably set up some other time. Okay, I'm not going anywhere this weekend. I'm going to be here. So that's it. So have a good weekend. Most probably I'll see you guys tomorrow. If not, then I'll see you guys on Tuesday.
I have a question.
Yeah.
Is the Zoom link for Friday is the same Zoom link?
No.
For
It's going to be a new Zoom link. Yeah.
Will you post it?
Absolutely. I'm going to post it on as an announcement.
Thank you.
All right. Anything else? Sorry if I was a little off today, but many of you probably know why I was off, but then it doesn't reflect on most of you. I just had a bad feeling that not everybody is taking the straight line path. I could be wrong, so I don't know exactly what happened on Canvas. I have no idea. Usually Canvas doesn't kick anyone out. It's probably a bad Wi-Fi or something. But then I'll see you guys tomorrow, if not Tuesday, okay? Reach out to me if you have any questions. I'll also upload some homework. Bye.